In this presentation, I will share with you our recent paper on how we use computation method to establish the design principles for sodium superionic conductors and how we use this design principle to predict and discover new sodium superionic conductors. There are a lot of interest in lithium and sodium superionic conductor because they can be used as a solid electrolyte to enable solid-state batteries. They have the potential to enable high energy density metallic anode and also improve the safety and other attributes of the battery. In addition to lithium solid-state battery, the sodium batteries also have a lot of advantages, such as the use of low-cost and abundant materials. They include the solid-state sodium battery, sodium sulfur battery, and those high-temperature molten salt batteries. There are a lot of interest in developing new materials because current solid electrolytes do not simultaneously satisfy all desired properties that are required to develop this new battery technology. In addition, there are limited availability of sodium-ion conductors, which impedes the development and innovation of these new sodium battery technologies. Here we provide a brief history overview for the discovery of sodium-ion conductor versus the lithium-ion conductor. You can see that back in the 70s, there are great sodium superionic conductors such as beta alumina and nacetylene. They give very high sodium ionic conductivity. But since the 90s, you see a lot of discovery of lithium-ion conductor, including garnet, argyrodite, thiophosphate, LGPS, all exhibit much higher lithium-ion conductivity. And more recently, discovery of this halide-based lithium conductor, which also show high ionic conductivity and many other great attributes. On the other hand, the development of sodium conductor has been greatly lacking. Mostly, we don't see any sodium conductor, maybe except for this one, have high ionic conductivity than nacetylene and beta aluminum. Also, if you look at all these great lithium conductor, people try to develop sodium counterpart of these materials, but they don't perform as well, such as the sodium version of the LGPS. And for some of them, such as garnet, argyrodite, they don't exist. For the halide lithium conductor, the sodium part also shows much lower conductivity. More recently, there are a lot of computation discoveries in the lithium superionic conductor space, such as this compound listed there. So here we compare the structures as ranked by the room temperature ionic conductivity for sodium conductor versus lithium conductor. You can see that the same structure perform very well for lithium superionic conductor, not as optimal for sodium conductor, such as LGPS, which shows a much lower sodium conductivity, and also these halide close packing structures, which also show poor conductivity in sodium. The best sodium conductor, such as beta alumina, shows much lower lithium conductivity. So our first question is, what causes these differences in sodium conductor and lithium conductor? These differences also tell us that the design principle developed for lithium superionic conductor may not be simply duplicated for sodium superionic conductor. So we would like to understand why is that, and how can we devise the design principle for sodium superionic conductors. Here we compare a few best performing lithium superionic conductor versus a few sodium superionic conductor. You can obviously see that their structure, the lithium-sodium coordination, and their diffusion channels are very different. So basically, we want to understand these differences and devise the design principles for sodium conductor. Let's first look at the design principle for lithium superionic conductor. So let's take LGPS, for example. If you look at these ions, sulfur, you can find that they pack in the body center cubic framework. The lithium occupy a tetrahedral site, migrate from one side to the next by crossing this triangle bottleneck. This gives a very low barrier. Similarly, if you have a sodium in this BCC ion framework, they also give a very low barrier. Across a wide range of lattice parameters, they both show very low migration barrier. The reason why this BCC ion framework works very well for fast ion conduction is that lithium takes a tetrahedral site. And when they go from one tetrahedral site to the next, cross a triangle bottleneck, there's no intermediate site. Also, the bottleneck size are very big. So as a result, it gives a flat energy landscape, hence the low energy barrier. Why does this design principle don't work for sodium-ion conductor? Here we analyze the coordination of sodium versus lithium in oxide, sulfide, chloride in the ICSD database. Sodium, in general, prefer a much larger coordination. 6 coordination, octahedral is much more common for sodium than their tetrahedral, whereas in lithium, there's a significant fraction of the tetrahedral side. This is true for oxide, sulfide, and chloride. Because sodium ion has a much larger ionic radius, so according to Pauline's rule, it prefers a high coordination numbers. And because of this preference, it makes the sodium less energetically favorable for the tetrahedral 4-coordinated side. That's why if you look all these sodium ionic conductor, sodium takes a much larger coordination side. This is the reason why the BCC ion framework would not for sodium, because they simply do not exist for sodium structures. Here we analyze a typical ion framework such as a face center cubic ion, which is from this O3 type sodium transition metal oxide, commonly used as a cathode material. And also this hexagonal close packing ion framework, HCP, which exists in this chloride lithium conductor. So in the FCC ion framework, the sodium migrates from this octahedral side, passing an intermediate tetrahedral side to the other octahedral side. It shows a very low barrier in lithium conductor, but it gives a very high barrier in sodium conductor. So the reason is because this tetrahedral side corresponding to here has a high energy for sodium transition, thus correspondingly give you a high barrier. A hexagonal close packing, it also gives a very low barrier for lithium diffusion, but it gives a very high barrier for sodium diffusion. Because of this narrow bottleneck given by these 3 chlorine ions give you the high energy barrier. So that's why these chloride are very good lithium conductor, but they show much poor performance in sodium conductor because of this narrow bottleneck. So how does this good sodium conductor overcoming this limit of the diffusion of this large radius sodium ion? Here we compare this O3 FCC ion framework versus one of these other polymorph, which is a P2 type sodium cobalt oxide. So we showed the O3 has the intermediate side and a small bottleneck framework. So in this P2 structure, it is known to give much higher ionic conductivity than the O3. The sodium sits in these prism sites, and they migrate from one prism site to the other by crossing this 4-coordinated bottleneck. So you have this phase sharing of prism site, and they pass through this much larger given by this 4 Rm. As a result, they gave a much lower energy barrier. Here you can see the advantage of this phase sharing high coordination site. Not only it's favorable for sodium ion, but as a result of that, you don't have an intermediate site, and your bottleneck is also large. You give a low energy barrier for sodium diffusion. We can summarize this phase sharing high coordination site as a key feature for sodium conductor. Here we plot the average coordination site in the diffusion channel and the percolation radius for all sodium conductor showing stars and the lithium conductor showing triangles. And the color code is their conductivity, where the yellow color means the high conductivity and dark blue color means low conductivity. As you can see here, the best lithium conductor is at the lower left corner with this 4 coordination in the diffusion channel, because that's given by the BCC ion design principle. For the sodium conductor, they have higher coordination number, 6 or above, and also a large percolation radius. For some of the other examples of sodium conductor, such as this sodium zirconium chloride, they have a HCP structure, but because of the low bottleneck given by the 3 chlorine ion, they have a lower conductivity. Similarly, for these 2 FCC ion framework, they have average coordination number of 5 in the diffusion channel because they average by 6 and 4. They also have this lower conductivity. For all the well-known superionic conductors such as beta aluminum, nasican, sodium antimony sulfide, P2, they all have both large coordination number and a large bottleneck size. So here we really shows that all sodium conductor does have this feature of phase sharing high coordination sites. Then we can use these two simple features to discover new sodium-ion conductor. By running a high-throughput screening using these two features, we indeed uncover all known sodium superionic conductor, such as nasicum, beta aluminum, and all these sulfide sodium conductor. And in addition, we discover 19 new structures with room temperature conductivity higher than 0.1 millisiemens per centimeter. One example is this based on U-chlorine-3 type of structure. There are a big family of compounds in this crystal structure. As you can see, the sodium really take this high coordination number and they are phase sharing. We have experimental collaborator confirm these compounds, and they are able to synthesize a large family of them with a total conductivity of 1 to 2 milliamens per centimeter, which is about 2 orders of magnitude than the previously known chloride-based sodium-ion conductor. We also have multiple oxide compound verified by experiments showing the bulk conductivity on the level of millisiemens per centimeter, similar to the previous best-known oxide superionic conductor. Therefore, we have multiple experiments verify the computation prediction and discovery of a new sodium-ion conductor. So with our work, we established the phase-sharing high coordination site as a design principle for sodium superionic conductors. In addition, we can also generalize this understanding. So why sodium-ion conductor works is that they provide this favorable site for sodium, which is a high coordination site, and their phase sharing provide no intermediate site and a large bottleneck that gives low energy barrier. So this is the same as a BCC ion framework, where lithium takes a tetrahedral site, transition to the same tetrahedral site with a large bottleneck size. Our understanding can also help you understand the non-BCC ion framework. Because if you look at the lithium garnet and also this nasicum, you have this large side. So for this large side, you can treat them as a split two tetrahedral. So the lithium still goes from one tetrahedral cross surface to another tetrahedral to another tetrahedral. In addition, this large side has been also reported in our previous paper to improve the lithium disordering. In addition, we find the side distortion also plays an important role. Previously, side distortion is reported to promote the lithium disordering. Here we also find that having the distortion would actually enlarge this bottleneck as observed in many of these sodium conductors. So that's another good feature of having side distortion commonly observed in these superionic conductors. I hope you enjoyed this presentation. You can refer to our papers for more details. Thank you.